Okay. I think I have to save out of all the chapters that are covered in this class, this is my least favorite. I'm not sure why this is. But we'll see if that leads to me getting it over with or not. But so I basically have this week to cover it, and then we get into ODEs, and that's a long chapter, and that's the last one. So, recording? Okay. So, this is chapter 11, Piecewise polynomials. Okay. So, the general idea is that if you have a bunch of points in the plane, like basically some function you want to fit. We're going to assume in this case that n is relatively large. And you want some interpolant that I'll call let's call it P of x. And by an interpolant, it means it agrees exactly with f at like given points. Now we know how to solve this problem already. We can pass a polynomial through all these points. So we have n plus 1 points altogether. We know that there's a polynomial degree n that matches. Except the problem with the approach that we know of is if we just let P of x be a polynomial, in other words, Lagrange interpolation that we're already familiar with, that can lead to large error. Because we have an error formula for Lagrange polynomial, and due to the high order derivatives, and also having this product of linear factors like x minus x naught, x minus x1, etc., that can also be large. You can make that part small using Chebyshev points, but even then you still have these high order derivatives. So even with Chebyshev, this can be problematic. So, so even though P of x would agree with f exactly at these points, in between those points, it could still be awful. But the thing is, we like using polynomials. They're so convenient. So what can we do? We have an impasse here. That we have a lot of data points. That's just using a high degree polynomial, but if we want that convenience, we also have to put up with large error. So one way to get a best of both worlds is piecewise polynomials. So the idea is if here are your points, here's your data, that you could find some polynomial of low degree, so this would be like P1, and then you have a different polynomial, and so on. So you define your function P of x to be equal to a different polynomial, different coefficients on each subinterval, and then you hook them all together. And you choose these polynomials to make sure that they fit the data points, and if you have any other flexibility, you can use that to maybe satisfy some other conditions. Like maybe you want to have not just a continuous function, but also a continuous derivative, something like that. So, and we're going to refer to these as splines. Although the term spline just comes from being a smooth interpolant. So it's really, the word spline has come from wanting smoothness and also interpolation. And we're not always going to have smoothness. It depends on what degree you make these things. So they're going to be, well, first, the term I need to describe is, and actually, I've just been running the section in my textbook on this stuff, and I found some mistakes, so hopefully I can find them in here too. So the degree of a spline is equal to, a spline called P of x is equal to the maximum degree of each polynomial that you include for each piece. Now, in the examples that I'll show you, we're going to choose the same degree for each piece. So that'll be the degree of the entire spline. And the idea is splines that we'll consider will be of low degree to avoid having these large errors that come with polynomial interpolation. Okay. Now, there are two degrees that we'll consider. Degree 1, or linear spline, and then degree 3, a cubic spline. Okay. I don't know if any of you play Words with Friends, or maybe you used to, and it just popped up on my phone. Word of the day, creepy. Like, oh, gee, thank you. Okay. I guess maybe a more pertinent question is, how many of you used to play that? And, well, yeah. So I only play with one person now, so I can wipe bother. Okay. So a linear spline, I can actually describe this pretty intuitively in 3 words. That once you have your points, I don't really need an x-axis for this, but whatever. Yeah, that it really is just that. That's intuitively how you would get it. That you just find the linear function that passes through neighboring points. And so I'm going to use this notation, the same as the textbook. S of L refers to a linear spline. And so the way we define it, I'll give you a different formula for each piece. So if x is between xi minus 1 and xi, then on this subinterval, I'll use Lagrange interpolation between those 2 points. So we have f of xi minus 1, and then I have a degree 1 Lagrange polynomial, x minus xi over xi minus 1 minus xi. And then for f of xi, I have x minus xi minus 1. Okay. So both of these are Lagrange polynomials, because if you plug in either one of these endpoints, one of these will become 0 and the other will become 1 to select the appropriate function value. And then, so depending on where x is within this domain, you use the appropriate formula. Okay. Now, these points, for interpolation, I'll refer to them just as interpolation points. When you're talking about splines, they have another name. Not sure how this came about. They're called knots. Or they might also be referred to as nodes. Like, we call them nodes for quadrature, so that term nodes is also used in other contexts too. So nodes, knots, interpolation points, all the same thing. Okay. All right, I'm going to skip this stuff because I just don't care. Alrighty. So there's a couple nice properties of linear splines. First of all, we can derive an error formula for them based on the error in Lagrange interpolation. And they also have an interesting smoothness property. And the funny thing is, the proof is in the textbook and in my notes, but I came up with an easier proof. Okay, so first, an error formula. We'll use a better piece of chalk. All we have here are these little nubs. I guess I just keep going from one little nub to the next. Okay.
Did Vivian steal them again?
What?
Did Vivian steal the good chalk again?
I guess so. So that's why she's not here. Okay. So the error formula, so on each piece, we have f minus the linear spline. And what I'm going to put here is just based on what do you get from Lagrange interpolation. So it'll be f double prime at some unknown point over 2, and then you have x minus each of the interpolation points you're using for this interval. So this is just Lagrange interpolation error. For the case of n equal 1, because we just have a degree 1 interpolant on that piece. Now, we can use this to try to come up with a bound on the error, because if I take this product of linear factors, so, well, first I'm going to define h sub I to be the gap between neighboring knots. And then I'm going to define h to be the maximum over all subintervals. So the maximum spacing between knots. Okay. Now, what I'm going to do is I want to find out how large this product of linear factors can get. So if I define a function g of x to be x minus x I minus 1 times x minus xi, and I'll find the extreme values of it. So I'll take a derivative, set it equals 0, and all that. So g prime is going to be, and I'm not going to multiply this out. I'm just going to use a product rule that's actually a little bit easier. So I have this times the derivative of that, which is 1, plus this times the derivative of that, which is 1. And that's going to give me 2x minus xi minus 1 plus xi, and I set that equal to 0. So I can solve this and get my one and only critical point is just the midpoint of the two. And I'll call that x star, so that's wherever the critical point occurs. And then what I can do is substitute this back into here. Now, what happens is, here are my 2 points. Xi minus 1, xi. X star is in the middle. So I'm going to have x star minus xi minus 1, x star minus xi. Now, what will happen is, if I look at these differences, since this is in the middle, the whole interval has a width of hi. So, what are these linear factors going to be equal to? Since x star is the midpoint. Half of? Yeah, so this one will be hi over 2. Where this one? Yeah, minus hi over 2. Now, it's only maximum absolute value that we care about. So this will be minus hi squared over 4. And the thing is, you only want the min or max on this interval. So you would check critical points, and you'd also check the endpoints. But what's the value of this at the endpoints? It's 0 because the endpoints are the roots. So that is as big as it could possibly get. Therefore, we can say that the error, for this I'll use the infinity norm, the maximum error on the entire domain that you're considering between x0 and xn, is less than or equal to, so we have the maximum of f double prime, which I'll use the infinity norm for that also, over, I have h squared over 4, but I also have a factor of 2 there, so I get h squared over 8. Where the infinity norm of a function in this case is defined to be the maximum absolute value between x0 and xn. So that's as large as you ever can get. And so we see that we have nice second order accuracy. No matter how many points we have, it's only the second derivative that determines how large the error can get. Whereas if we're doing regular Lagrange interpolation across all these points, we'd be looking at the n plus first derivative, which could be enormous. Okay, so any questions about where that error formula comes from? All right, so it's just working with Lagrange. All right, so now one other property of linear splines I'm going to define Sobolev space. And so what terms of our function is Sobolev space is that so if f is in this space, so this is definition, so if and only if. Okay, so its kth derivative belongs to L2 of AB. By L2, which, and now this is another function space of interest, where so this describes instead of all functions such that if you integrate the function squared over AB, it's actually it's square integrable. Okay. All right. Now, so this is one condition, that the kth derivative has to be square integrable. Now, it's not necessarily going to be continuous. You get a function that has like jump discontinuities and it can still satisfy this. And the other condition is that its k minus first derivative is absolutely continuous. And what I mean by absolutely continuous is meaning at its derivative, so fk, is finite. And here's an abbreviation that comes up now and then. AE, which means almost everywhere, in the interval AB. And what I mean by almost everywhere is the set of points where this doesn't hold, they'd be like isolated points. Basically has no width to it, no size, measures 0. So there's only a smattering of points where this breaks down. That's like barely worth considering. Also, it has to be integrable on AB. Although we already have a square integrable, so that's not a problem. We also have that the integral of fk would be on a typo in a note, so I'll have to fix that later. Hold on. Basically, the fundamental theorem of calculus applies to it. That you can just take the antiderivative and plug in limits, and that is equal to the integral. It would be equal to the integral. Okay. All right. Now, is absolutely, if a function is continuously differentiable, that implies that it's absolutely continuous. But it is not an if and only relationship. So you give a function that is absolutely continuous, but it might fail to be continuously differentiable. So what's happening here is fk minus 1 is itself continuous. It's basically like a stronger form of continuity. But it is not continuously differentiable. This derivative exists almost everywhere, that it's not, but this derivative could fail to be continuous. So that's important distinction there. So what that means is, okay. So that would mean that the set of all functions that are continuously differentiable k times on an interval is a proper subset of the corresponding Sobolev space. So in other words, being in the Sobolev space, HK is a slightly weaker condition than being k times continuously differentiable. Okay. So that was quite a roundabout thing to do. Actually, I almost didn't do it, but it turns out I need to do it for this next result. Okay. Because what I'm particularly interested in is like any linear spline belongs to H1. So because so in other words, a linear spline itself is absolutely continuous. And it has a derivative, it exists almost everywhere in the interval. But at the knots, there's the derivative does not exist because we have a kink in the graph in that case. But it is something that where integration works. Okay. So I need this Sobolev space for k equals 1 to describe, to state this latest result about how derivatives of linear splines behave. Oh man. I was here the whole time. Oops. Sorry, Vivian.
Oh.
Okay. So, here, have a definition of a Sobolev space, Vivian. Okay. Dang it. All right. Yeah, well, I didn't really want to do any of this anyway, but mathematical rigor. Okay. Okay. So one result we have about linear splines is if V is in H1 of AB, so meaning that so V is absolutely continuous, and V prime is in L2 of AB, so it is square integrable. Okay. All right. So, and I should mention everything else on the previous board is on page 108 in the notes. Okay. From function space definitions. So if V is in the space, then another assumption, and also V interpolates F at the knots. So V could be the linear spline, for instance, because it's in H1 of AB and it interpolates F at the knots. But there are other functions. You could define many other functions, infinitely many functions, like higher degree polynomials that have this property also. But what we can say is that the derivative of the linear spline, the 2 norm, is less than or equal to the 2 norm of V prime. So in other words, so SL is, we can say, the flattest interpolate of F in this sublet space. Now that's important because you don't want to have, if you're going to have some interpolant of F, you don't want its derivative getting out of hand. Like, for instance, Runge's example. You would have crazy amount of steepness between points, and you want to try to rein that in. So, so this says that the derivative is as small as you can get among all functions that pass through the graph of F at the knots. Okay. All right. Now, so I can try like a simpler proof than what the textbook has. Okay. So what I can do. How much time have I wasted? Okay. I can write the 2 norm of V prime to be, okay, so I have V prime minus SL prime plus SL prime. And then if I group these together, then I can use properties of inner products. So I have the norm of this squared plus 2 times the inner product of this with this. Plus the norm of that. Okay. Now, I want to focus on this cross term right here. Because, so since that's an inner product, I can express that as an integral. So B prime minus SL prime times SL prime. Now, since the spline, this is a linear spline on each subinterval, it is a linear function. So what can I say about SL prime?
You said SL prime is a linear function?
SL is a linear function.
So what can you say about SL prime?
Yes.
It's a constant.
Yeah, it's a piecewise constant function. Now, on each subinterval, it's a different constant, but the point is it's constant. So that means we can pull out the integral. So on each subinterval. So I break this down into integrals over subintervals. So this one part I'll just pull out. SL prime at well, let's see. The thing is, at the knots, the derivative is well. I'll do this. SL prime of x is equal to a constant, which I'll call m sub I, at least in the open interval, in the interior. We can't see what it is at the endpoints. And that slope would just be f of xi minus 1 minus f of xi over xi minus 1 minus xi. All right. Now, so what I can do is I can pull that out on each subinterval, and then what's left? I have v prime of x minus m sub I again. Now, I can go ahead and, whoops, my endpoints are wrong. That's xi minus 1 up to xi. Okay. So now I can go ahead and evaluate this integral. So I have mi factored out, and then this will be v of x, just taking the antiderivative of this. And it helps that it's an h1b, h1 of ab that allows me to do this. Minus mi x with limits xi minus 1 and xi. So now I can go ahead and plug in the limits. So what I'm going to have is v of xi minus v of xi minus 1 minus my slope f of xi minus f of xi minus 1 all over xi minus xi minus 1. So that's the slope times the difference of these limits, xi minus xi minus 1. Now, can anyone tell me how this simplifies? Keep in mind, what do we know about f? That's right. What about what we know about v? Well, what else do we know about v?
It's equal to f.
Right. So how can we take advantage of that in here? Yeah, so this, I can say this is f down here.
Oh, don't those cancel out?
Yeah.
X's? What is it, 0?
Yeah, it's 0. Yeah, because, yeah, v's will, now that these are gone, these v's.
Yeah, those will cancel out.
Yeah. So the whole thing is 0. So that cross term is 0. So now, if I go back over here, okay. So the conclusion is the norm of v prime. So with this term gone, that's equal to the norm of SL prime squared. So norm of v prime squared is equal to norm of SL prime squared plus another norm. V prime minus SL prime squared. But the thing is, I want to show that this one is smaller than this. Well, if this plus something non-negative is equal to this, that would tell me that the norm of SL prime is less than or equal to the norm of V prime. Because the only way I could get to the norm of V prime was to add something positive onto it. Okay. That's why it's necessary to show that this cross term as 0, because normally this is something that could be positive or negative. Okay, so any questions about that? Because in the textbook, started out the same, that proof, gets down to this point, and then does integration by parts. Like, why? And then you get a second derivative of SL, which is 0. But yeah, it just seemed a bit overkill. It's like, okay, go figure. Okay. Now, let's see. Okay, so that's, okay, we have a last thing I need to prove about linear splines. I'm going to fall behind again, aren't I? Well, we'll see. Definitely not calling on anybody anytime soon. Because I'm calling on you once per semester. Okay, because I only have you two left, right? Okay, well, still. You agree to that? Okay. Yeah. So, yeah. Vivian is what I was writing on the board earlier. And yes, now you have it on tape, but I just needed to define this function space, sublove space, to state the assumptions properly from a proof I just did. So the long and short of it, I mean, you have my audio not mixed with video description earlier, but the point of this is a space of functions that's almost the same as functions that are k times continuously differentiable. It's just that being k times continuously differentiable is a slightly stronger condition than what it takes here, which is all we need for the theorem that I just proved. And I probably could have gone with just continuously differentiable and saying, okay, we have a slightly weaker result. But this is what it means to be in a Sobolev space, that if it's in HK, then the kth derivative is square integrable, and that's what that means. And the k minus first derivative is absolutely continuous. And this definition is given here in the notes, but everything you missed on this board was just defined as function space, so I could use it in the statement of what I just proved. Okay, so sorry about the mix-up. Now, okay. Now, another way to describe a linear spline is, instead of using Lagrange interpolation in each piece, you can actually describe it as a linear combination of functions. You can say SL of x is equal to a linear combination of the function values you're trying to fit times these basis functions, phi of x. And these are called hat functions. They play a similar role as Lagrange polynomials. Each one is equal to 0 at all the knots, except for one of them where it's equal to 1. So the idea is, here's a hat function for x0 that's equal to 1 here, and then linearly goes down to 0 and stays there. Then for x1, it goes up to y equals 1, and then back down at x2, and then stays 0 after that. And then, so you have more hat functions after that. So they all have this graph that looks like a pointy hat, and that's where it gets its name. Of course, Stephanie, remember dealing with those fond memories from summer. Yeah. So we can actually use Lagrange interpolation to write down formulas for these. So for instance, the first one, so between x0 and x1, it would be, so it would be x1 minus, well, okay, x minus x1 over minus h1, where recall the definition of spacings. Each subinterval has width hi, so h1, h2, h3, and so on. So that's what it is on that first interval, and I'm just using Lagrange interpolation here. And it's equal to 0 after that. Okay. So that's the first hat function. It's really only half a hat function. And then the ones in the, and at the other end, the last hat function also has only two pieces. It's equal to 0 for x up to x n minus 1. And then between xn minus 1 and xn, we have so that way, if you plug in x equal to xn, we get hn, and it cancels out and gives you 1. So those are the two half-hat functions on the boundary, and then all the ones in the interior have to be defined in 4 pieces. So 0 up to xi minus 1. It's also equal to 0 after xi plus 1. And then in between we have, starting from, okay, so this has to be, yeah. So between xi minus 1 and xi, it has a slope of 1 over hi to get up to 1. And then it comes down after that. So x minus xi plus 1 over minus hi plus 1 for x between xi and xi plus 1. So by using Lagrange interpolation on each subinterval, we define these basis functions, and since they're equal to 1 at one of the knots and 0 at all the other ones, then we can just take linear combinations of them where the coefficients are just the function values for a function you're trying to fit. So it's quite convenient. So this is another way to construct a linear spline.
For the two end ones, the first ones we
Yeah.
did, why is the first one x minus x1 and then the lower one x minus xn minus 1?
Oh, that's where they're equal to 0.
Okay.
Yeah, because here at x naught, we want it to be 1.
Okay.
Yeah. So yeah, we always pick a neighboring point to be the root.
Right.
Okay. And actually, you kind of draw parallels between these non-zero pieces here and the non-zero pieces here.
Is the middle one, third one x minus xi plus 1?
Yes.
Divided by h of I plus 1? Negative.
Yes. Okay. All right, I'm doing on time. Okay. So that's all I have to say about linear splines. Now I can at least get started on cubic. Ugh. Well, things get particularly tedious because when you get the higher degree polynomials, you have, because you can describe a piecewise linear function on each piece using just two coefficients. Your y equals mx plus b. But for a cubic, you have 4 coefficients on each piece.
I just understand the indexes for h. Like when x is in between x0 and x1 is minus h1, but when x is between xn minus 1 and xn, h is n.
Okay, the reason for that, if we look at the graphs. So for instance, for this one, this is our only piece. It's sloping downward, so it has to be negative. And then when we get to the very end, at xn, it's sloping positive. And same here, like these, like going up, going down. Because these differences, I've way of written these as Lagrange polynomials. Oh, wait a minute.
No, I asked about indexes, not the
Okay.
minus and positive sign.
Okay, hold on a second. I'll make sure I didn't screw anything up. Wait. Okay. All right, for these. Okay, I'm sorry, can you repeat your question?
I mean, for me, indexes are not consistent. Like in the last one,
Yeah.
in the end point is the index of h, but the first one, again, the last point is the index.
Okay, so
Okay, I mean, makes sense. I got it.
okay, yeah, because they come from the different halves of a hat. So yeah, here the indices agree, here they differ by 1. So because of how I define h, they differ by 1 for sloping up, and their indexes agree for sloping down. All right, cubic splines. All right, now, the way I'll define a cubic spline is, I'll call it S of x, and then on each piece, I'll call it Si of x. So for x between xi minus 1 and xi, I'll use the same convention for numbering the points. Now because it's cubic on each piece, we have four terms. And the way I'll write it is our constant term ai plus our linear term and then, but I'm not going to write it in power form. That'll be too inconvenient. I'll have it start at the end point of its own interval. Will serve basically as an origin. Okay, so here's the form we'll use for each piece. Okay. Now, we have more flexibility. We only need a linear function to agree with the data, but so whatever conditions can be satisfied from this much flexibility. So first of all, so the conditions that we'll impose on this cubic spline, first, well, it has to fit the data. So S of xi must be equal to yi, which is the notation for f of xi, so let's abbreviate them as y's. Okay. Now, what that means is, if I plug in x equal to xi minus 1, then all these terms are going to go away. So I have so this immediately tells me what the a's are supposed to be. And that's going to be true for n. So here, I have n pieces. So I only goes from 1 to n, not 0 to n. Okay. So that at least nails down those coefficients. However, I've not yet accounted for the last data point, yn. I haven't guaranteed that that'll be satisfied. Also, I need to have continuity because all I've ensured is that each piece, its left endpoint will have a correct value. I haven't done anything about the right endpoint. So I'll take care of that now with continuity. So I need to have on each piece Si of xi, which I would define, which if I plug in xi into here, I'm going to get ai plus bi hi plus ci hi squared plus di hi cubed must be equal to, from this condition, yi, which I can also define as ai plus 1. Here for notational convenience, I can say an plus 1 is equal to f of xn. I don't really need this coefficient, but it's just so this relationship makes sense. For I equal 1 to up to n. Okay. So this makes sure of two things. One, it fits all the data, and second, that the spline is continuous on the whole interval. But I have 4 coefficients per piece. That means I have 4n coefficients total. I've only imposed 2n conditions, here and here and here. I have 2n left over. So I can be greedy and establish more constraints. So what I want is, I want s prime to be continuous. So if I take the derivative of this, so I want s I prime at xi. So the value of the derivative at the right endpoint of each piece to equal the value of the derivative at the left endpoint of the next piece. But how does that translate into coefficients? So if I take the derivative of this, I'm going to get, okay, so bi, that's my constant term. Then here I have my linear term, 2ci, and then I plug in x equal to xi, which gives me hi. And then over here, I differentiate this, and I get 3di, and then I plug in xi, so that would be hi squared. So that is equal to the derivative at the right endpoint of each interval. And this has to equal the derivative of the next piece. Well, if I take the derivative of this and I plug in the left endpoint, everything's going to go away except for the b term. I'll get bi plus 1. Now, this has to be imposed at the interior knots. And I only have n minus 1 of those. So I equals 1 to up to n minus 1. Now, I'm going to gloss over steps here, but I'm just going to write down the derivatives over here. So it's bi plus 2ci x minus xi minus 1 plus 3di x minus xi minus 1 squared. So what that means is, if I plug in the left endpoint, these terms will go away and it's get bi. If I plug in the right endpoint, xi, that's when I get these linear factors become equal to hi. That's where base conditions come from. Sorry, I glossed over too much. Okay. Any questions about this one, this condition? We can do the same thing. Well, because here I only have n minus 1 more conditions. Now I have a grand total of 3n minus 1 conditions. I have n plus 1 left. So I can also require s double prime to be continuous. All right, so off to the side, I'll compute the second derivatives. So si double prime, okay, that goes away. I have 2ci plus 6di x minus xi minus 1 squared. So if I plug in the left endpoint, what am I going to get? Yeah. And if I plug in for right endpoint, it's similar to what just happened for first derivative. What will it give me in that case?
Ci plus 60i h squared, hi squared.
Oh, wait, I goofed. That's the first power. Yeah. Okay. Everybody see where it comes from? And the rest of you, feel free to voice answers too, or give it a shot. Don't be shy. All right. So now I want si double prime at xi equal si plus 1 prime at xi. So here, well, I have written down over there. So that's 2ci plus 6di hi is equal to, now in this case, I don't have that double prime. I don't have it written down over there except if I just shift the indices, I have si double prime at xi minus 1. So the index differs by 1. And I can use this as long as I shift the index back. So that's 2ci plus 1, I equals 1 to up to n minus 1. So again, you can only impose this at the interior knots. Okay. So we have 4n degrees of freedom. We've used up 4n minus 2. I have 2 degrees of freedom left. Yes?
But I must be from 1 to n minus 2 or n minus 1?
N minus 1. Because, so at least this way we go up to Cn, which is valid because we have n pieces altogether. Now, what can we do with those last 2 degrees of freedom? There's actually some choice. So I'll mention a couple boundary conditions that we can impose. All right. Now, okay, so one choice is called, there are actually several terms for it. They're called free boundary conditions, or natural boundary conditions, or not boundary conditions. Not sure where that one comes from. So any of these terms apply. And the conditions are that the second derivatives have to be 0 at the endpoints of the whole domain. So if that happens, that would immediately tell you that the C1 must be 0. And for the other one, you have 2Cn plus 6 dn hn has to be 0. Okay. So that's one kind, and this is kind of most people use. The other is called clamped boundary conditions, where if you know the derivatives of f at the endpoints of a domain, then we can require that these conditions are satisfied. So in terms of coefficients, that tells you that, B1 must be equal to f prime and x naught. And the other condition is that Bn plus 2cn hn plus 3dn hn squared must be equal to f prime and xn. So now we have 4n coefficients, 4n conditions. So this will allow this cubic spline to be uniquely determined for whichever boundary condition you choose. Now, all of these equations for all the coefficients, we have these, and the two boundary conditions over there, whichever ones you want, you could set up a system of equations. Two equations, like 4n equations, 4n unknowns. So you have like a 4n by 4n matrix. But you actually can work with a smaller system than that. Because for one thing, the A's are already known. So actually what I'll do is, I want to keep these equations up. All right. Okay. Oh, good. I'm almost out of time. So I'm tired of covering this. All right.
I don't
So,
think I've ever heard you say that.
what?
Ever. Oh, good. I'm almost out of time. It's usually shoot.
Oh, yeah. Well, because I know I'm not finishing this today anyway. I still have plenty to cover on Wednesday. So
Yeah.
the hell will continue. Okay.
Make it sound so appealing.
Anyhow. Oh, God.
Abdullah?
Yeah. I was going to think about now. Yeah. Okay. Because what we can do is we can actually eliminate everything except for the C's, and we'll just set up a linear system to solve for them. So if we can figure out everything else, then we're good to go. So we already know what the A's are. So each A is equal to... All right, so that's set. Now what about the next thing we can solve for are actually the D's. So I have a condition for second derivatives, 2ci plus 6di hi is equal to ci plus 1. So I can solve that for di. Okay. So, all right, so now the A's and D's are eliminated. And then I can use the condition for continuity of the spline itself to eliminate the B's. So I have AI, which is really yi minus 1, plus bihi plus cihi squared plus, now I know what di is now, equal to a is equal to yi, which is the same as ai plus 1. Now let's see. Okay, something's amiss here because all right. If I pose this for 1, 2, up to n, that seems kind of strange because I have a cn plus 1 here, which is not really part of my spline. However, cn is equal to f double prime at xn. So I could make that, actually it's over 2. But the thing is, in the case of natural boundary conditions, that'll just be 0. Now, if it's clamped, you have a little bit more to work around, but at least we have this approach to defining the d's. Now, okay, I should probably sort it out later, but anyway. Well, y's are known. So I can use this to solve for the b's. Now first, I'm going to simplify this. I can say bi is plus ci hi. So I'm canceling out hi throughout. Plus ci plus 1 minus ci over 3 hi. Because I canceled 1, and then I cancel another from the whole equation, is equal to yi minus yi minus 1 all over hi. So now what I can do is I can solve for bi. So that would be yi minus 1 over hi, and then I have minus 2ci minus ci plus 1 hi all over 3. I'll make sure I did that right. Okay, actually I have this formula in a note, so let me make sure it's equivalent. Okay, so over hi minus, okay, that should be a plus. Okay, yes. All right, and as long as I have a definition for, this is for I equals 1 up to n, as long as I have some sort of definition for cn plus 1, which again, sorry, cn. Sorry. Oh, dang it. Sorry. This should be cn plus 1, not cn. Okay. But again, that would be 0 in the case of natural boundary conditions. Okay. So I have the a's, d's, and b's all settled. So now what I can do is I can take this bi and substitute it into here and also in here to get, at least for the interior points, in order to get, let's see, actually, this one is defined, yeah, for I just 1 to n. So if I substitute this into both instances of b's, where I shift indices accordingly, then I can get an equation for only involving the c's that are unknowns, and then the y values that are already known. So what I would get is y I minus yi minus 1 over hi. Now, this is going to be, oh, okay. That's going to be a little bit strange. Well, b, okay. All right, plus 2CIHI. Oh, I'm out of time. Okay, that's probably for best. I would take it as part anyway, because I was afraid I'd screw up. So, we've eliminated A, D's, and B's. We'll handle the C's starting on Wednesday.